Okay, let's implement this part together. To calculate the gradient, we better start from the later part of the network. And to calculate the gradient in respect of W2, it is quite easy. What we do is D1 dot and D1. Because here, we are multiplying D1 and W2, and we just receive the upstream gradient and then multiply the coefficient D1 here. And that is going to be our gradient for W2. And what is the gradient for B2? It is simply because it is a add block. What we are going to do is just receive the upstream gradient and take the sum operation. And to calculate gradients for W1 and B2, we need to calculate intermediate gradients. That is going to be dA2. It is going to be MP dot dy and W2 dot t. So we need to calculate the gradient in respect of WA2 and then in respect of Z1. Then we are going to be able to calculate gradients for W1 and B1. So that's why we are calculating gradients for A2 and Z1. And the gradient for dZ1 is going to be sigmoid gradient dot A1 times dA2. So this is upstream gradient for Z1. And gradient for W1 is going to be simply MP dot X transpose dZ1. This is the upstream gradient for W1. So here, it receives upstream gradient from Z1. Okay? And B1, we do the same thing. We perform MP dot sum dZ1 along the axis 0. And the thing is, here we use analytical gradients. However, we can put this mol layer or add layer to implement our two-layer net. So you can perform these operations using these modular layers. That's also possible. Okay, and let's implement this. Let's see how we can do this with this code. I'm going to borrow some sigmoid grad, softmax, and sigmoid from already defined code base. I'll just copy this code here, and the warning will disappear. Softmax. Softmax like this. Let's run this code. And this one as well. So after you modularize the computational blocks, you can put these layers into this two-layer net and check whether they are working perfectly or not, as expected or not. All right. And this is the code base to download the data set. After class, you can have a look at this if you're interested. Okay, let's use our two-layer net and this data set. This data set is called MNIST. It is similar to CIFAR. It has 10 classes. First thing is, we need to read data set. E is the label, and list. And we need to pass some parameters like normalize. Normalize means we are normalize the pixel values of the input image. And one hot label is what we talked about in the class. And we're going to define our network as 2-layer net. And when we flatten the MNIST images, it's going to have the size of 784. Here we are going to use the hidden size of 50 and output size as 10 because we have 10 classes. We're going to iterate the learning process for 10,000 times. The train size is going to be the total number of training examples. And we're going to use batch size of 100. And learning rate or the update step size is going to be 0.1. And I'm going to keep track of the train loss, train accuracy, and test accuracy. And the iteration per epoch is going to be train size divided by batch size. Okay? Then that is going to be how many iterations we need to perform for each epoch. And for each iteration, what we are going to do is first get the batch mask. So we are choosing random samples from our train data. And we mask our train data with our batch mask. Then originally X-train contains like 50,000 images, but after masking, it will contain only 100 images because we have batch size of 100. So that's what we are doing here. All right. And the mask should be applied to the labels as well. And we can calculate the gradient by calling the gradient method of our network by passing our samples like this. And for our parameters, we need to update our parameters. And here we are using minus sign because we are moving in the opposite direction of the gradient to reduce the loss. And we need to use the learning rate here. This is the step size and grad key. Okay, that's how we update our network. And to keep track of how well our network is doing, we're going to calculate the loss. And also, so we are going to append this loss value. And for after each epoch, we are going to, so for after each epoch, we're going to print out how well our network is doing. This is going to be chain accuracy. And test accuracy is going to be next test. We are passing the test data set and calculate the test accuracy. And we store these values. And after training is over, we're going to plot these values. Like this. And in the middle, we're going to print out how well our network is doing. Chain accuracy and test accuracy. And we're going to format this so that it will print out only 4 numbers. This formatting is very useful. Otherwise, it's not that beautiful. Okay, so this is the training code we basically use. Most of AI models follow this type of training code. We first load the data, initialize model, and for each epoch, we retrieve the data and then perform the learning process, updating the parameters, and then we log the process of training like this. And after the training process is over, we're going to plot the results. And we're going to do markers. So we are plotting the accuracy of training set. And we're going to plot test accuracy. With different line. Like this. X label is going to be epochs. Y label is going to be accuracy. And the accuracy cannot exceed 1. We are setting the XY limit as 1. And we are adding legend at lower right position and show the result. So when we run this, it downloads the images and then convert our images. Something went wrong. I think I need to find where it went wrong. There was a typo here. We need to set this as T, not Y. And let's run this again. This again. And as you can see here, the accuracy improves quite fast. Takes about like a minute to train this network. And in the first epoch, the accuracy literally jumps. However, at the end of the training phase, the update size decreases. And this is the plot we made. And the accuracy jumps, and then the update size becomes smaller. And at the end, we achieved about 95% of accuracy, which is quite satisfactory. And the thing is, we just used very simple network. Our network is not that complicated. However, it can achieve quite good accuracy. It's a very simple network.